Welcome back to Mathematics 0110. This lesson is about something called increasing and decreasing functions. When we see a graph like the one on the left-hand side, we want to be able to qualitatively and quantitatively describe its major features. Qualitatively, we may want to think of the graph in terms of a context, to say maybe this graph represents the height of a roller coaster as you're moving from the left to the right. So on the left-hand side, we might have started at a height of 12 meters, and then the height starts decreasing, so we're going down a hill until we get to the bottom of the hill, and then we start climbing the hill, so the height starts increasing again, then we get to the top of this hill, and then our height goes down once again. Or it may describe a bank account. More money at the beginning, and then it goes down to zero, and then up, and then becomes negative. So that's a qualitative description of the graph. A quantitative description would be something like saying it's decreasing in a certain region. It's decreasing specifically, as far as we can tell, from minus infinity all the way to zero. And then it begins increasing from zero until some x value. It's hard to tell from the graph without knowing what the algebraic form is, without knowing what the f of x that represents this graph actually is, but it is increasing between 0 and 4 over 3. And then afterwards, it's decreasing. We can merge the two descriptions together, the qualitative and the quantitative, by labeling a graph like this with arrows. So to say that it's decreasing in the first region, increasing in the second, decreasing in the third, or even putting the labels of the arrows directly labeled on the graph, as indicated there. Now, there's a connection between this idea of increasing and decreasing in slopes of tangent lines. Anywhere where a function is decreasing, the tangent line in that region, in that whole region, is going to be negative. It's going to have a negative slope, rather. And then in a region where the function is increasing, all tangent lines at all points in that region will have positive slope. So again, negative slope tangent lines indicate where a function is decreasing. Positive slope tangent lines indicate where a function is increasing. So you can probably tell where this is going. We're going to go and connect derivatives to increasing and decreasing, which is no surprise. A derivative is a rate of change. And when we talk about increasing and decreasing, we're really talking about rates of change. So we can condense this, almost not quite the approach, but we're building an approach to determining where a function is increasing, where a function is decreasing, based entirely on whether the derivative of the function is positive or negative in each particular region. The problem is, how do we know how many regions there are? Maybe we know the function has a negative slope tangent line at x equals, let's say, minus 5. And it's still negative at x equals minus 3. How do we know that it didn't turn positive somewhere in the middle? So we're going to need some strategy to determine where can a function switch from increasing to decreasing, or vice versa. We'll get to that, but first I want to look at two functions that you know what they are, you know how to graph them, they're both straight lines. I want to make sure that this strategy that we have for determining where a function is increasing and decreasing actually matches up with that experience that we have. So in these questions, we're asked to find the interval where the function f of x is increasing and the interval where it's decreasing. So I'm gonna just take the derivative. F prime of x is equal to 5 minus 0, which is 5, which is positive. And notice that this is positive for all x values. So f prime of x is always positive. That means the function is always increasing. This makes sense. This is a straight line with a slope of 5. Positive slope of 5 means the graph is going from bottom left to top right. So if that was a bank account, that would be the bank account growing with time. The next one, when we take the derivative Derivative of 20 is 0. Derivative of negative 5x is negative 5. We get negative 5 as the answer. This is negative for all x values. So f prime of x is always negative. And then that means f of x is always decreasing. And that makes sense as well. This is a line with a slope of negative 5. So it's a decreasing function. It's going from top left to bottom right. Going back to the qualitative picture, we are still answering this same question about where is the function increasing, where is the function decreasing. We can do it this way, algebraically. Notice I didn't draw any pictures. We determine where a function is increasing and decreasing just by taking a derivative and checking to see if the derivative is positive or negative. And it's identical in end result to analysis where you look at a graph and say, well, this function is increasing here, decreasing here, increasing here, and then decreasing here. I'll be a little bit more specific. I'll put it in words or put it in math. I'll say this f of x is increasing in the following intervals. Increasing on the interval from, it looks like minus infinity all the way to minus 1. And then it's increasing again from 0 to 2. And f of x is decreasing on the following intervals, on the interval from negative 1 to 0, and the interval from 2 to infinity. So that would be determining the regions of increasing and decreasing given a graph instead of given a function. The step that's equivalent is checking for this derivative being positive or negative is the same as checking whether the y value is going up or the y value is going down as we go to the right. Sometimes it's messy, like this one. We have a function with a discontinuity in the middle. This is called an infinite discontinuity or a vertical asymptote. So I'm going to be a little bit more careful here when labeling the different pieces. The function is also given. It's not a very nice looking function, but we don't, for this example, we don't need to work with the function. We can work directly with the picture. So let's see, the first part, it's decreasing at least from A to B. So I'll label that as we go. Decreasing. It could be. I'll just indicate the answer in terms of the letters that are here. It's also going to be true further out. Decreasing on the following interval. So far we have from A to B, and likely from negative infinity to A as well. Where else is it decreasing? We'll look at from C to D, it's decreasing. Y value is going down there, so from C to D. And it's decreasing from D to K, up here. Y value is going down. Now notice that those two regions, those two last regions there, they are different regions. They're not one continuous part of the number line from C to K. There's a break at D, at the discontinuity. So I do need to write them separately. And that's it for the decreasing side. Now I'm going to talk about increasing for this graph. For increasing, we see one region of increasing is from B to C. And we see another region of increasing is from K onward, from K to infinity. So I'm also going to say it's decreasing probably from negative infinity to b. And I'll say that includes a to b. It includes that part of the number line. So again, when you're working with discontinuities and talking about regions of increasing and decreasing, you can't treat that whole part of the number line as one continuous region. And I'll give you the real reason why you can't do that. Down here, oh, there's my dot. So down here, the y value is extremely negative on the left-hand side of D. And as you go to the right-hand side of D, the y value jumps up. So it's not correct to say that the function is decreasing in that entire region of the number line all the way from C to K. It's not. It's decreasing from C to D, and it's decreasing again from D to K. And then it teleports from the left side of D to the right side of D, increases in value, but because it's not a region of the function, like we can't draw a curve that connects that very negative y value to that very positive y value, it's not a region of increasing or a region of decreasing. It's not a region at all. So what's here is all that we can say. Okay, next is our recipe. So I mentioned that this is great if we know what all the regions are. If we have a graph, we know what all the regions are just by looking at it. If we have a simple function like a straight line, there's only going to be one region, and it's either going to be always increasing or always decreasing. Or maybe we're told what the regions are, like in this graph, they were labeled for us. But how do we get that labeling? Like, how do we tell where a function could possibly switch from increasing to decreasing? How do we tell what the different regions are if we're given not a graph, but given an algebraic function? So here's what the recipe is. We're first going to take the derivative of the function. Then we're going to set the derivative equal to 0. The reason we're setting it to 0 is if a function switches from increasing to decreasing, for example, then the derivative is going to go from positive to negative. And what number is between positive numbers and negative numbers? 0. So we're just looking for the number that's in between positives and negatives. We're just looking for where does that function's derivative equal 0. We're also looking for where does that function's derivative not exist. So this one's kind of misleading. This is also where the function doesn't exist, but there can be situations where, oh wait, never mind. Yeah, it's kind of both, but it's mostly where the derivative is discontinuous, where the derivative has a DNE, where let's say you have a division by 0 or some other type of problem. What we do next, and the text here isn't very good, but we create a number line. We create a number line and we cut that number line up at all the solutions we found in step 2. So at all the x coordinates that caused the derivative to be 0, and at all the x coordinates that caused the derivative to not exist. Then we do a test. So we cut our number line up. That's subdividing it up into regions. Then inside each region, we know that the function's either always increasing or always decreasing. So all we have to do is perform a diagnostic check on the derivative of the function at some test value that's inside that region. So some test value that's between the endpoints of that region. We pick any number that we want inside a given region, plug it into the derivative, and we check, is the outcome positive or is the outcome negative? If the outcome of that evaluation is positive, it means the function is increasing in the entire region. If the outcome is negative, it means the entire function is decreasing in that entire region. And ignore the text. It's best to see this in action through an example. Also, before we get into the examples, there's some vocabulary I want to mention, that any location where the derivative of a function is equal to 0 or where the derivative of a function does not exist, those x values are called critical numbers. A critical point is, so like all points, it's an x coordinate comma a y coordinate. The y coordinate comes from plugging in the critical number so the x value, into the original function. So plug critical number into the original function. So the x coordinate of the critical point is the critical number. I'll be using this vocabulary throughout. So we'll do a quick example. Determine the critical numbers and the open interval where f of x is increasing and where it is decreasing. So here's our process. So I'm going to go in the same order as these steps. There's 4 steps. Step 1, we're going to take the derivative of the function. So f prime of x is 3x squared minus 6x minus 24. Then step 2, so going back to it, step 2 is to set the derivative equal to 0 and check for where the derivative does not exist. So 0 is equal to 3x squared minus 6x minus 24. And note, 3x squared minus 6x minus 24 exists for all x. There's no division, so we can't end up dividing by 0. Not possible to divide by 0, etc. So all those other domain violations, we can't have them happen. It's a polynomial. And then what was step 3? I'll go back to my checklist. Step 3 is to create open intervals. So I'm going to make a number line. This is why I said not to bother reading that, and I didn't read it either. Oh, we're not done yet. We're not done step 2. Getting ahead of myself. So we have to set this thing equal to 0 and solve for x. How are we going to do that? Well, let's start by common factoring. I'm going to common factor 3 out. X squared minus 2x minus 8. Now that's a quadratic. I'm going to factor it using the product and sum method. I want a multiplication of 2 mystery numbers to give -8 and an addition of the mystery numbers to give -2. And what will work is -4 and +2. That means we get 2 solutions. We get, so if left-hand side is equal to right-hand side, so if left-hand side is 0, right-hand side must be 0. How can that happen? That can happen either if the first thing here is 0, which is 3 is never 0, it's always 3. Or it can happen if x minus 4 is equal to 0. That's going to happen if x is 4. Or it can happen if x plus 2 is equal to 0, and that will happen if x is -2. So if any one of those pieces on the right-hand side is 0, then the whole right-hand side will be 0 and will match the left-hand side. Okay, now we have our solutions. We have our x coordinates. So we can answer part of the question. X equals 4, x equals -2 are the critical numbers. Now we have to figure out where is the function increasing, where is the function decreasing. So I'm going to make a number line. And this is the part that weirds a lot of people out, because you have freedom, you have choice. And freedom in math is unusual. Just kidding. You only think it's unusual, but it's not. So no choice so far. We have to make the number line. I'm putting the number line over the entire domain of the function. Since the function is a polynomial, its domain is the entire number line from -infinity to infinity. I'm cutting it at the solutions that we found. Now I'm going to choose test values. So the test values I'm going to choose are any number from -infinity to -2. Oh, also notice I put them in order. You have to put them from the lowest to the highest. So that's really important. Okay, now pick any number you want from -infinity to -2. -7. Sounds good to me. I have no complaints about -7. And I didn't pick -3 on purpose, because who cares? You can pick any number you want. I'll show you why. Now I'm going to pick another number between -2 and +4. Any number you want. I'm going to pick 3. I'm not even going to pick it in the middle. And then what's next? I need a number between 4 and infinity. How about 11? Okay, and those are our test values. Why did I choose those? Any number will do as long as it fits inside each of those regions. What do we do with them is we evaluate the derivative at each of the test values. Evaluate f prime of x at each test value. So f prime evaluated at -7. That's going to be 3 times -7 minus 4, -11. Oh, I better write it all in. -7 minus 4, and then -7 plus 2. So that'll be 3 times -11 times -5. Go ahead and multiply it out if you want. All that we care about is it positive or is it negative? We have a positive times a negative times a negative, so it's going to be a positive overall. And that means it's increasing. So I'm going to put a little up arrow there. It's increasing on the entire interval from -infinity to -2. And I'm going to continue the question in the next video. I'm going to shrink the text down to be able to fit everything on.